A rev counter for a racing car must be able to work really fast. And today I show you how to develop an Arduino controller that allows to reach the maximum stepper motor speed. A stepper motor can spin really fast if you have a proper acceleration control. However, if you want to process volatile signals and still want to achieve maximum speed, this is not entirely trivial. And that's because you have to take into account that the stepper motor has to be decelerated with every change of the direction and then accelerated again in the opposite direction. Today I will tell you a few tricks on how to do this with an Arduino-based controller. The datasheet for the X27 stepper motor contains two specifications for the maximum speed. First, we have the start-stop value of 200 degrees per second. And this is the maximum speed of the stepper motor from a standstill. With this speed, the stepper motor can stop with a single step and turn into the other direction in the next step. By the way, we are talking here about the maximum speed that the motor can only reach with a minimum mass moment of inertia. If the motor has to drive a large pointer or a heavy shaft, then the speed is significantly reduced. Second, we find the value for the maximum operating speed with appropriate acceleration. It is 600 degrees per second. This is 3 times the maximum speed from a standing start. We can reach it if we accelerate and decelerate the motor appropriately. With NEMA motors, which are much larger and more powerful, things are more complicated. And by the way, with larger stepper motors, you need a stepper driver that can supply the currents that a larger motor needs. Here you would actually have to consider the mass moments of inertia of the arrangement and the torque characteristics of the motor to find the speed parameters. However, the same principle can be applied to a larger motor. I will shorten the reasoning here because I just wanted to show you the way to do it. For example, a reasonable range for the NEMA motor could be between 200 and 6000 half steps per second, corresponding to 180 and 5400 degrees per second. In this case, the speed could be increased by a factor of 30, provided that a suitable acceleration and deceleration can be implemented. That's why we are going to discuss the Arduino code that is just doing that. With our stepper motor, we want to approach target values that can change frequently. As an effect of this, the motor has to change its direction of rotation, just as we have seen with the pointer instrument. If we want to use the maximum speed of the stepper, then we have to decelerate and accelerate the motor accordingly with each change. To understand this better, let's look at the slow motion simulation I made with the Arduino IDE's serial plotter. In that clip we see the target value in magenta, the position of the stepper motor in blue and the stepper speed in green color. And the position value follows the target value with a defined speed controlled by our Arduino. The speed is low at the start and increases to maximum speed once the stepper motor has started, while the target value is moving upwards. When the position of the stepper motor approaches the target value, then the motor has to be slowed down to the starting speed. This way, our stepper motor can follow the target value without losing steps. Okay, that seems to be working pretty well for this simple process. We were literally always waiting until the stepper motor had reached its new target position. But what happens if we don't wait for a target position to be reached, but constantly get new target values? Is our controller then resilient enough so that our stepper motor does not lose any steps? We are now looking at this situation in slow motion in our simulation. That doesn't seem to be a problem either. Now random target values are coming quickly. This is a kind of worst case scenario, because a new target value comes before the old target value is reached. The stepper motor is constantly forced to change its direction. Our Arduino controller can handle this as well. The speed is actually reduced to such an extent that the stepper motor can constantly start and stop even with changed direction. The realization in the Arduino code cost me quite some experiments. And many of my ideas, which I don't even want to tell you all about, just didn't work to my satisfaction. Sometimes the stepper motor accelerated kind of shaky when the target value was changed slowly. Sometimes it didn't accelerate at all. Sometimes it just humped, etc. Ultimately, the solution is simpler than I thought. You really just need the right idea for it. And I will explain it to you now. By the way, I'm using the same code as a basis that I have used before for other projects. So the main loop is the same as before. We read an analog voltage, which is processed for our target value. And then comes the lighting. You saw at the beginning that the project has special signal functions, which I will explain to you later. And then our target value is computed from the analog input signal. We have already seen the startup function, the clipping function, and the drive stepper function in earlier episodes. They are only adapted to the new project. And then comes our new function that controls the acceleration of the stepper motor. Let's take a closer look at it now. First, I want to prevent the target value from jumping fast between low and high values. With these two lines, we achieve that our target value can only increase or decrease a certain number of steps on each iteration. The variables slope steep backward and slope steep forward define these numbers separately for backward and forward direction. Incidentally, this is an interesting option for a pointer instrument if, for example, you want to set the pointer's backward movement to be significantly slower than the forward movement. Now comes the real trick. We calculate the speed of the stepper motor depending on the distance from its current position to the target value. With the variable ac steps, we defined the number of steps for acceleration. The following two lines simply limit the maximum and minimum speed. Here is another tip. Assuming a stepper motor can start-stop at the speed of 100 steps per second, then the further acceleration up to the maximum speed should be smaller than that. If the maximum speed is 600 steps per second, then you need at least 5 steps for acceleration. The driver stepper function works with the delay time between the steps, and therefore we convert the speed into the delay time. And that's it. And this works great for me. Now, as promised, we check out the lighting feature because I think it looks really cool. The first two rows turn on 4 white LEDs that are supposed to illuminate the dial. The brightness can be adjusted via the variable. One output of the Arduino Nano should not be loaded with more than 20 milliamps, so I use 2 output ports for the 4 LEDs in order to reach the brightness that I want. You saw at the beginning that the red LED lights up as soon as a certain position value is exceeded. If the position value becomes even larger, then the red LED flashes with greater brightness. This is achieved with the operations in the following lines. And before the red LED lights up, the yellow LED appears as a kind of pre-warning, similar to the pointer instruments of an insane fast sports car. I'm currently considering using such instruments for a slot car track. That would not only be a cool gimmick, because the spectators could use it to follow how fast the slot cars are racing along the track. In addition, one could compare the competitors better with each other. If you want to make your stepper motor work really fast, this is the way to go. And for a maximum overall performance, you still can play with the speed parameters and the acceleration steps. I'm planning a further Arduino control that can actually measure the rounds per minute. And a nice 3D printed case and different dials for the instruments are coming soon. Happy making! Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.